All right, looking at the top of page 7, number 9 here says we've got to plot r equals 1 plus 2 sine of theta. Using what I know about the graphs we just previously tried, I know this won't exactly be a cardioid because your A and your B here are different numbers. A does not equal B. Now, it'll be some sort of limacon shape. Another thing I know just by looking at it, since it's in terms of sine, I know that if it is some sort of heart shape or limacon shape, it should be symmetric with respect to a vertical axis of symmetry. All right, let's give this a try. I'll label my quadrantals just to get my bearing. So I'm at, we've got 0, we've got pi over 2. So 0, pi over 2, pi, and then 3 pi over 2. Okay, now the point plotting. Again, feel free to pause the video and fill in all these points on this table on your own. I'm going to go through them, just starting one by one, plugging in that theta value. 1 plus 2 sine of 0. So 1 plus 2 times the sine of 0, which I know is 0, and you get a point at 1. So my first point is going to be at 1 comma 1. And I think as long as you're labeling each ring as worth 1, that's okay if we don't show what each check mark is worth. But 0, 1 is going to be the first dot that needs to get labeled. Pi over 6 plugged in gives you 1 plus 1, which is 2. I'll keep going and fill out all of quadrant 1. So you get 1 plus the square root of 2, which is about 2.4. For pi over 3, you get 1 plus the square root of 3, which is about 2.7. And then to round out the quadrant, for pi over 2, you just get exactly 3. Okay, let's plot those. So 1 comma 1 we've already plotted. Pi over 6 comma 2. Here's pi over 6, and here's us coming out 2 units. Pi over 4, we're up 2.4. So just eyeballing in between 2 and 3. And then pi over 3 is going to be 2.7. So pi over 3, 2.7. Curve it around. And then pi over 2 is up at 3. And one quadrant is done. Let's see some symmetry on the other side. Some of these values you're going to recognize. If I plug in 2 pi over 3, I get 1 plus square root of 3 again. I get 2.7. 3 pi over 4, 1 plus the square root of 2. So you're going to get 2.4. 5 pi over 6 gives you exactly 2, and pi gives you exactly 1. Okay, so that helps with quadrant 2. Let's go down, start with 2 pi over 3. 2 pi over 3, 2.7. So skip a line to 2 pi over 3, and then come out 2.7. Okay, 3 pi over 4, 2.4. And then 5 pi over 6, comma 2. And pi, comma 1. Have a lot of symmetry this time with relation to this y-axis here, this y-axis symmetry. Now I wonder if we're just going to get repeats like that other graph where we didn't have to fill out the entire table. Check out 7 pi over 6. At 7 pi over 6, it's 1 plus 2 times negative a half. You're actually going to get 0 for 7 pi over 6, and you have a dot right at the pole. Okay, I'm dying to know what happens. With 5 pi over 4, you get 1 minus the square root of 2, which is roughly negative 0.4. With 4 pi over 3, 1 minus the square root of 3, which is about negative 0.7. And then 3 pi over 2 to round out the quadrant gets you down to negative 1. Let's start here. 5 pi over 4, negative 0.4. Here's the original 5 pi over 4. We want to flip-flop to the other side, to the pi over 4 line, and we want to come out 0.4. So we're flipping over here, we're coming out 0.4. We're about pretty close to the pole in there. 4 pi over 3 is down in quadrant 3. We're going to flip up to pi over 3, and we're going to come out 0.7. So 0.7 would be more like that. 3 pi over 2, negative 1. Here's 3 pi over 2. Flip yourself up to the pi over 2 line and come out a unit. It's like you have a little inner loop right inside of that outer one that we just created that was bigger. Let's finish it out with quadrant 4. 5 pi over 3, exact value, 1 minus the square root of 3 again. So about negative 0.7. You'll get another repeat for 7 pi over 4. 1 minus the square root of 2, so negative 0.4. 11 pi over 6 is going to give you 0 again, and 2 pi, we've already plotted. It's going to give you 1. So to finish it out, 5 pi over 3 is over here. We're coming flip-flopping across to 2 pi over 3, and we're coming out we're coming out 0.7. So we'll be about there. 7 pi over 4 is negative 0.4. So here's 7 pi over 4. We're flipping over to 3 pi over 4. and we're coming out 0.4 here. And then you have a dot at the pole at 0 and a repeat of a point that we already had before. What does this look like to you? I'm hoping it looks like kind of like that last cardioid, but it's got an inner loop on the inside. So let's connect the dots. We're going to try to do this in a smooth curve. I'll do the inner loop first. So you have this loop on the inside, and then can you curve it around and give it a loop on the outside? And this is another type of limacon. It's a limacon with an inner loop. Limacon, fancy C, we'll say with inner loop. It didn't get to be a complete cardioid heart shape like the last example because A and B were different values. You have a 1 and a 2. So here's how a limacon with inner loop gets generated. You have R equals the same general form, A plus or minus B sine of theta, or A plus or minus B cosine of theta. But what makes it have that inner loop is the fact that you're going to say A is less than B. Anytime A is less than B, like in this case, A is 1 and B is 2, you get the loop on the inside, symmetric with respect to a vertical line as well. This would be a good one to practice converting with too. So I'm going to give that a try in the little space I have at the bottom here. Let's try to convert to rectangular form. So you have R equals 1 plus 2 sine of theta. Okay. What should we do? Well, for sine of theta, you can plug its definition, y over r. So r equals 1 plus 2 times y over r. It's good because it got a y in the mix, but I have recognized that I still have an r to get rid of. So what we might want to do now is multiply everything through by r. It'll give you an r squared on the left side, and it'll give you something that you can work with on the right side, and we'll do something more with it in a second. So this will be r squared equals r, I think, plus 2y once the r gets distributed to the entire expression. Now we've got to get rid of these r's. And for the first one, we can plug in x squared plus y squared. And for the second one, it's not so pretty. It's going to be the square root of x squared plus y squared. And then plus the 2y that's sitting there as well. You have successfully converted this to rectangular form, right? We have all x's and y's now, no r's and thetas. What you're going to want to do to make it look better is just get rid of the square root. So we can start that off by isolating the square root. X squared plus y squared. And then we can carefully square both sides. That's what I want to try next. So I want to square the left side and square the right side to get rid of the square root. And we can leave the left side inside of parentheses. X squared plus y squared minus 2y squared equals x squared plus y squared. It's a little bit preferable to have it in this form because there's no more square root there. And all of this was just good practice with the algebra of converting. Okay, number 10 at the bottom of page 7. The way it originally reads, we have to graph r equals 2 cosine of 3 theta. I actually want to change the problem, and I want to swap out those two constants. Can you rewrite it as r equals 3 times the cosine of 2 theta? So I'm switching the 3 and the 2 the way they appeared originally. Okay, now we've got to graph this. This one's a little different from the others, but still a good idea to label everything quadrantal. So 0 or 2 pi, pi over 2, pi, and then 3 pi over 2. When we go to plug in points here, remember that you are multiplying the theta by 2 every time you go to plug in. So for instance, let's plug in 0. It won't make much of a difference. But 3 cosine of 2 times 0 gives you 3 times the cosine of 0, which is the number 3. But when I go to plug in pi over 6, I get 3 cosine of 2 times pi over 6, which is actually pi over 3. And exact value-wise, I get 1.5 for the next one. If I plug in pi over 4, I get 3 cosine of 2 times pi over 4, so pi over 2. And here I'll get the constant 0, okay? I'm going to fill out the rest of the exact values. To save time, I'm going to pause the video. I'd like you to pause the video now, fill out the values, and then come back and join me. So here they go. Negative 1.5. I'm just going right down the table. Negative 3, negative 1.5. 3 pi over 4 is 0. 5 pi over 6 is 1.5. Pi gives you 3. 7 pi over 6 gives you 1.5. Almost done. So 0, negative 1.5. A lot of repeats here. 3 pi over 2 gives you negative 3. 5 pi over 3 gives me negative 1.5 again. 7 pi over 4 is 0. 11 pi over 6 is 1.5. And then last but not least, 2 pi gives me 3 again. Let's see what these crazy points look like. I'm dying to know this shape. So here goes nothing. We've got each ring representing a unit. So you come out 0, 3 for your first point. Then we've got pi over 6, 1.5. So skip a line up to pi over 6, come out 1.5, and put a dot. Pi over 4 is 0, so we're back at the pole. Pi over 3 gives you negative 1.5. So here's pi over 3. Here's where we're flipping down to, this would be 4 pi over 3. And we're coming out 1.5. So we're kind of jumping all around every time we hit these negative radius values. Pi over 2 gives you negative 3. So we're up at pi over 2. We flip down to 3 pi over 2, and we're coming out 3 rings. 2 pi over 3 is negative 1.5. Here's 2 pi over 3. Here's where I'm flipping down to 5 pi over 3. And here's 1.5. Okay, 3 pi over 4 is 0. We already know about that one. 5 pi over 6 is 1.5. 5 pi over 6, 1.5. All right, halfway there. Pi is 3, so pi 3. 7 pi over 6 is 1.5, so 1.5 will come right there. 5 pi over 4 is 0. We already knew about that. 4 pi over 3 is negative 1.5. So here we are at 4 pi over 3. We're flipping up to pi over 3, and we're coming out 1.5. 3 pi over 2, negative 3. Here's 3 pi over 2. Here's pi over 2 where we're flipping, and then we'll come out 3 units. 5 pi over 3 is negative 1.5. So 5 pi over 3 is down in quadrant 4. Flip up to 2 pi over 3 and come out 1.5. 7 pi over 4 is 0, no big deal. 11 pi over 6, 1.5. So 1.5 is here. And then 2 pi over 3 is a point that we already, 2 pi 3 is a point that we already knew about that was here. Now, what do these points look like to you? Could you connect them in kind of like a star? Is it pointy? Is it curved? Well, this is going to be a rose. It's supposed to look like a flower, which is kind of nice in the springtime to talk about flowers. It's supposed to look like a flower when all said and done. And the rose has 4 petals. Okay. If I were to be a little bit more careful, I'm just going to give you a couple of extra points that we didn't know about already. And if I were to be a little bit more careful, and if I plotted it every 15 degrees, I would actually get points at 2.6 and negative 2.6 every time I plot one of these. These blue points I'm just adding because I decided to plot a few extra just to give myself a little bit more of a picture of it. And you're going to get, I want you to curve this, and we'll experiment with this. I want you to just draw a rose that goes through these. I'm going to draw a vertically oriented petal first. You've got one that's right underneath of it symmetrically. You've got one that's off to the side. And then you've got one that's over to the left. This was a good one for us to try together. I also knew what this was going to look like. I had this picture in my head. It's up to me that it looks more curved and less pointed. The more points you show, the more curved this picture will look. A rose is going to result every time you have an equation of the form r equals a cosine a certain n times theta, or r equals a sine of a certain number n times theta. And I want to say something about the petals. Though this 3 that was out front, do you see something about 3 in the picture? Do you see how each of the petals has a span of 3 units, up, down, left, and right? That happens, that's no coincidence. It happens because A equals 3. So that's going to tell you how big the petals are. This is going to give you something about the number of petals, n equals 2. If n is even, there are 2n petals. So we had an even n value. N was 2, so we had 4 petals in this rose. If n comes out to be odd, you actually have just n petals. There are n petals. So if I had left this equation how it originally looked, the 2 cosine 3 theta, it would have been a 3-petal rose as it was originally. Okay, thanks a lot. Have a good day.